Alright, let me begin with a little video here about how to map a point x in Rn to another point y in Rn by an invertible matrix. So to keep it interesting, we're going to assume they're both non-zero. Because otherwise, the only way to map x to y is if they're both zero. So let's suppose they're both non-zero. And what we'll do is we'll take the vectors x and y, put them position 1, position 2, and then extend that to a basis of Rn. That's the way to do this. And then I'll show you the map here. So then looking at the picture, we basically have this situation here. So I've got x, I've got y. I want to get from x to y. What I can't, I mean, there are arbitrary vectors, so that's kind of a pain. But it's much easier to think about E1 and E2. See, if I have E1 down here and E2 down here, I can easily get from E1 to E2 by the matrix, which just puts E2 and E1 in the first two columns, and then E3 through En in the rest. See, because then M of E1 is equal to E2, because the first column of M is E2. All right, so this matrix is it's easy to think about how to move E1 to E2 by an invertible matrix. It's a little bit trickier to think about how to move x to y by an invertible matrix, but not that tricky. Here's how you do it. So I take x, I map it down to the coordinate vector, x beta. I take y, map it down to the coordinate vector, y beta. That gives me E2 and E1 respective. I know I can get from E2 to E1 by left multiplication by that matrix. And so I just follow this path. I go down here, then across there, and then back up there again. So the composition works in opposite order. So we first of all do the last thing, which is phi beta inverse, and then left multiplication by m, and then phi beta comes first. Now these are all linear transformations from Rn to Rn, so as such the matrix of their composition is the product of the matrices of the transformations composed. And let's see if I have it in frame here. I think I got it. Yeah, we fit. So there it is. So I just make A equal to the product of the standard matrix of the coordinate map inverse, the left multiplication by m, and the standard matrix of the coordinate map. But of course that is the inverse of the coordinate map matrix, which, by the way, the coordinate maps matrix is the basis matrix inverse. And so likewise this becomes just beta, and so we've just got the product of this, that, and that. Which of course you could explicitly calculate rather if you actually had a specific x and y. You could, certainly do this. You could implement this calculation if you wanted to. And there it is. So a times x is this times that, but x beta is e times m is E2, and then you've got E2 times the basis matrix. Well, that's exactly the second thing in the basis, which is y. So there you have ax equals to y, and it should also be clear that since A is the product of the matrices of invertible maps, it follows that the determinant of A is not equal to 0, or if you like, A is an element of GLN. Now this is the thing I asked you guys to try to work out at the end of class one day, and I never quite circled back to it, but well, here it is. This is what's needed to prove that the action of the general linear group on Rn is transitive. This shows that there's two orbits, basically. 0 maps to 0, and anything non-zero maps to anything else non-zero. So well, it's not a transitive action, I guess, on all of Rn, but it is a transitive action on Rn with 0 removed. So anyway, thanks guys.